Welcome back. In this video I would like to show you one of the 2D experiments, 2D NMR experiments, and this is possibly the easiest that is around, even though it has a very fancy name. It's an HSQC, which stands for Heteronuclear Single Quantum Correlation. In basic terms, it's nothing else than a cozy type experiment between a proton and a carbon. So what we see in this type of NMR experiment is how carbon atoms are connected to hydrogen atoms through one single bond. You could use the same type of experiment also for other heteroatoms. So for example, carbon to nitrogen would work, or nitrogen to hydrogen, or whatsoever. The important bit is that we have a single bond connecting those two atoms. The scales here below we have on the horizontal a proton scale, and vertical we have a carbon-13 scale in this case. We see also already the traces here. However, if you look at this carbon-13 spectrum, it looks quite poorly resolved. It comes straight from the HSQC experiment, and here we see the proton, which also comes automatically in the experiment. If you want to select something better, we can again use a setup. And in this case we know we have been running a depth queue, so we can select this depth queue here and put it onto the vertical line, which is quite nice because then we get the up and downs again. And we can also put on the horizontal one our external proton. So this has happened. Then, as it is a cozy type technique, we can again use our middle mouse wheel to increase or decrease the depth of the spectrum. Again, we can go down quite substantially until we only see the so-called crossspots. Something is different to the cozy. First of all, we don't have this diagonal setup. Instead, we see little islands, and each single island is basically showing us how a signal in the proton spectrum is connected to a carbon atom. In the same way as we could zoom the trace in or make the peaks bigger in the cozy, we can again use the middle wheel to increase or decrease the size of the signals, and we can also again zoom in by using the letter Z, and then we get this view here. Just go back. Something else is different here. If you look closely here, we see a lot of islands, and one island is different in color. And this comes from the type of carbon atom. We remember here, if you look at this area, if I zoom this one in, one of those signals was a CH2 group, and the CH2 group has a different sign in its HSQC, and this one gets a different color that is just set here for the software. I'm going back to the full spectrum. What else can I see or can't see? Obviously, the quaternary atoms are not connected to any hydrogen atom. So this is why the spectrum is also cut off, because there is nothing here on the far end. So we don't see any cross peaks from the quaternary signals. So if you go along here, we can verify this one again by using the cross tool. So again, we can just go from one peak to another one to another one. This time we don't need the shift button. What else can we do? We can actually do some peak picking. So we can hit the letter K and then zoom, or this looks like zooming, and circle all our signals here, and then we get all the data here. I think it makes sense to zoom a little bit. I'm going for the aromatic one. What we can see here, these are very weak peaks, so we can ignore those here. But the bigger ones here, the 7.21 is corresponding to the 127.28 or whatever signal. So the signal that is more here to the right or to the top, and the other one is connected to the other peak. So this time we have a bit more information about who is linked to whom. If we go back to the whole spectrum, can take some other signals here, zoom them in, forget about the small ones here, because obviously the signal is only the one in the middle. but we can see that this one here is connected to this peak here, and that is about 44.9. So forget about all those decimals, because the system has a bit of problems, because it will now try to see the connection between each single part of the peak of the full signal. So this is what we can do with the HSQC spectrum.